This video series is about Unit 1, Module 5, which will deal with elements and compounds. Before we get started, we will cover the learning objectives for this video series. We will be interpreting chemical symbols for isotopes and ions. Then we will learn about how to calculate atomic mass using the percent abundances of different isotopes. Then we will learn about the arrangement of elements on the periodic table. And then we will move into compounds, learning differences between molecular and ionic compounds, and how to tell whether something will be molecular and have covalent bonds or whether something will be ionic. And then we will learn how to apply nomenclature rules to name our different compounds and to write chemical formulas for different compounds. Our first topic will be on chemical symbols, and the learning objective for this video is to interpret chemical symbols for isotopes and ions. Before we do that, we should define what our different elements are and what's different about them. So in our previous learning unit, we knew that elements had a nucleus. Atoms had a nucleus in the center of the atom that contained protons and neutrons. What makes an atom of gold different than an atom of carbon is the number of protons in the nucleus. All atoms of the same element have the same number of protons in the nucleus. So all gold atoms will have the same number of protons in the nucleus. Gold has 79 protons in the nucleus, and a carbon atom only has 6 protons in the nucleus. This number of protons in the nucleus is known as the atomic number, which is given the symbol, the letter Z. Why Z, I do not know, but it's Z. All elements also have a 1 or 2 letter symbol in order to describe that element. So we've named all of the different elements and given them 1 or 2 letter symbols to abbreviate their name. Gold is given the symbol AU, which is derived from its Latin name, and carbon is given the letter C. If we do have a 2-letter symbol, then the first letter is capitalized and the second letter is lowercase. That's to differentiate between elements like cobalt and capital C, capital O, which is carbon monoxide. So capitalization is very important because it's the difference between having a metal element and a toxic molecular gas. When we write our atomic symbols, then we have our 1 or 2 letter abbreviation in the center. 1 or 2 letter. So that's where we would write like the AU or C. And then we would write the atomic number in the lower left corner, which is equal to the number of protons. A stands for the mass number. I don't know why mass number starts with A, other than we have too many M's in chemistry, and so mass has a second letter of A. The mass number is equal to the number of protons plus the number of neutrons. And so since this is a count of things plus another count of things, it's always a whole number. We know a proton is approximately 1 atomic mass unit in mass, and then a neutron has a mass of about 1 atomic mass unit. So by adding the number of protons to the number of neutrons, we end up with a number pretty close to the actual mass of the atom, but not exactly. So mass number is not the actual mass. It's just an approximation of the mass. And it's always a whole number. The actual mass is not a whole number. Then over in the top right-hand corner of our atomic symbol, then we have the overall charge. The overall charge has to deal with our charged subatomic particles. And so we have to add up how many protons we have and subtract out how many electrons. So now these are counts of things. You can also think of like, hey, protons are positively charged. And so if you have +1 times your number of protons, then you can add that to -1 times your number of electrons to get the charge from the electrons. And so if this is equal, if you have the same number of protons as electrons, then that adds up to 0, that adds up to 0, that adds up to 0. So you're net overall neutral. And we don't write a 0 for the charge if it's neutral. If it's neutral, it will just be blank there. But if we have excess protons and not enough electrons, then that's an overall positive charge. And then if we do have to write out how many extra. So like if we have 2 extra positive charges, then we would write 2 positive as the charge. If we had extra electrons, then it would be overall negative charge. And so that would look like this. So let's say that we had 5 electrons and only 3 protons, then that would be a 2- overall charge. Typically, we write the magnitude followed by the direction. So the 2 comes before the positive, the 2 comes before the negative. That's a detail that is just by convention. So our different elements are defined by the number of protons in the nucleus. But we have another subatomic particle in the nucleus called the neutron. Neutrons can vary within the same element. And so all of these atoms have 1 proton. And so that means it's an atom of hydrogen. But this nucleus has 0 electrons. And so its mass number is just 1 because it only has 1 proton and 0 neutrons. This atom has 1 proton and 1 neutron. So its atomic number is still 1 like the previous atom, so it's still hydrogen, but now its mass number is 2 because both protons and neutrons contribute to that mass number. Now, for this other one, this is known as tritium, but it's a different isotope of hydrogen, where it still has 1 proton in the nucleus, so it's still 1, and it's H there, so it's still hydrogen, but now it has 2 neutrons. So all 3 of these subatomic particles contribute to the mass number, so it has the mass number of 3. Now, most hydrogen atoms are this isotope. And then small percentages, very small percentages, are these other isotopes. This one's like almost nothing, but this is given the code name deuterium, and so you can find like deuterated water is used to absorb nuclear radiation in nuclear power plants. Deuterated water means that it has a higher percentage of this isotope of hydrogen compared to regular hydrogen. So water is H2O. Water made with deuterium and water made with hydrogen, the only difference that you would notice between water like that we know as water and water that's deuterated is the mass. So regular water that you're used to, and if you had a sample next to it, like same volume of water, you would notice that the deuterium oxide, the deuterated water, has a much higher mass if you're going to be comparing these samples side by side. So let's do a practice problem. For this practice problem, you will need your periodic table out. So go ahead and pause the video to find your periodic table. And when you're ready to continue, then go ahead and unpause the video to double check your work. So the practice problem says, how many protons and neutrons does the atom of lead 206 have? This 206 refers to the mass number. Lead has an atomic number of 82. So since its atomic number is 82, then the number of protons is equal to 82. The number of neutrons will be equal to our mass number, and then we will subtract out the 82. So if we subtract those two, then we end up with, I think we have 124. Let me double check that by actually typing it into my calculator, because I'm a little bit paranoid. Yeah, it's 124. Good old math. I should have put this slide before the previous slide. But yeah, that number afterwards is the mass number. And so cobalt 60 would have, if we write out its notation, that 60 is the mass number, so that's a superscript. And cobalt has an atomic number of 27. Carbon, that's saying its mass number, so that's its mass number is a superscript on the left-hand side, and its atomic number would be a subscript there. So now we've learned that atoms are defined by the number of elements are defined by the number of protons in the nucleus. We can have different isotopes if we vary the neutron count, and we can have different ions of the same element if we change the electron count. And so atoms by default have the same number of protons as electrons. That way they're overall neutral. And so a regular atom of sodium has 11 protons and 11 electrons, so that it's overall 0 charge. A sodium ion would have lost this outer electron here, and so that's gone. And so it's missing 1 electron. So now it has more protons than electrons, and so it has an overall charge of +1. And so when we write our chemical symbol for that, then we would be writing Na+. They wrote the 1 here just to emphasize to you as a newbie that it is 1 positive charge, but really the 1 is implied and we don't write the 1. And if it's no charge, nothing is written. So if it is a positively charged ion is a generic term to mean any atom that has a charge. So this is a sodium ion. This is a sodium atom. So this ion here just means it has a charge to it. So the nucleus is the same, number of electrons changed. Ion means it's charged. Ions with an overall positive charge are called cations, featured by this cute little kitty cat up here. So it might help you to remember that cations are the ones with positive charge by picturing this adorable kitty cat that also has a positively charged tail, because cats have paws. Anions are negatively charged ions, and so you can remember that by the first 2 letters, because a negative ion is an ion. And so if it's negative, it means it has extra electrons, and if it's positive, it means it's missing electrons. So let's do an example problem. I will pull out my periodic table here. And so which element is it? Well, it's silicon. How many protons is it? Protons are given by this, which is 14. That's its atomic number. How many neutrons? Well, to find neutrons, I have to do the mass number minus 14. And so that would be 15. And then how many electrons? There is no charge written. And so therefore it's neutral. So if I do 3 dots, it means therefore. I'm not sure if that's how you spell therefore, but therefore it's neutral. So since it's neutral, we have our number of protons must equal our number of neutrons. And so I must have 14 electrons. All right, here's our last practice problem for this video. So go ahead and pause the video to try to work out these 3 problems. Each row here is a separate problem. When you think you have the table filled in, then go ahead and unpause the video to double check your work. Okay, let's go over this. So we know that for this symbol, the atomic number is given by this subscript. So my atomic number must be 22. My mass number is the superscript, which is 48. And so there must be a mass number of 48. The number of neutrons is equal to my mass number A minus my atomic number Z, because I know protons plus neutrons equals atomic number. So 48 minus 22 is 26. There is no charge written up here, so it must be neutral. Nothing written there. And so its number of electrons has to be equal to the number of protons to make it neutral. So let's work out our next one. So for our next one, we're not given the symbol, so we'll have to work that out. The first thing that we can figure out is the atomic number. And so we can do that based on the number of electrons and the overall charge. This overall charge tells us that we have 3 extra electrons. So 3 extra electrons. So we have 54 electrons, and so 3 minus that would tell us that we have 51 protons. Now we can figure out our number of neutrons, because our mass number minus 51 is equal to our number of neutrons. And so then I can work out my chemical symbol. So I can go to my periodic table and find out what's atomic number 51, and that is antimony. So atomic number 51 is antimony with a mass number of 122 and my overall charge of 3 minus. For our next one, we have our atomic number and we're missing our mass number. So my atomic number 3 is lithium. And I know it's an overall charge of +1, but I'm missing the mass number. The mass number is going to be equal to my protons plus my neutrons, which is equal to 8. So that's 8. Now, I wrote that whole symbol out, but I still have to fill in this number of electrons box. Since it is +1 overall charge, then that means that it is 1 extra proton. Or I could say missing 1 electron. 1 more proton than electron. That means that this has to be 2. So then we can go through the PowerPoint presentation and verify that all of my thinking was correct. I gotta fix that. That's a typo. That's not true.